Polynomial inequalities, and our last example, a rational inequality, require a little bit of a different approach than our linear inequalities when it comes to solving. Instead of directly finding the boundary values and then immediately knowing which direction based on the inequality symbol that we have in the problem, whether it's going to be to the left or to the right of the boundary values, or even in the absolute value inequalities, the and or variety, we have to basically find all the key points where the boundary locations are, and then we have to use our just a test to check to see which areas of the number line represent numbers that are included in the solution set and which are not. So, for example, if we take the first one here, what I'm going to do is I'm going to rethink it as an equation rather than an inequality. So I'm going to ignore the fact that it's an inequality problem because I just want to find the points on my number line that are going to divide the number line into regions that I then need to test to see if they work or don't. So this one's going to be factorable, so I'm going to break it up into a couple of sets of parentheses. So I've got x multiplying to make a negative, so I know I have one of each. I've got to multiply to make 6, but have a difference of 5, so that means it's going to be minus 6 and plus 1. So I'm going to set each of these equal to 0. I've got x plus 1 equals 0, and x minus 6 equals 0. So my key points, as I'm going to describe them, are the solutions to this quadratic. So it's x equals -1 and positive 6. And so on my number line, I'm going to label those locations. I'm going to put -1 here, I'm going to put 6 here. And so with those 2 points, I essentially have 3 regions in my number line. I've got what's going on over here, smaller than -1. I've got this middle section here between -1 and 6, and then I have everything that's greater than 6. So I have 3 separate regions. So I'm going to have to test to see whether the points work or don't work in my inequality in each of those regions. And so I'm just going to do that by picking a number and testing it. So if I start with the left-hand side of my graph, I can test, let's say, -5, something like that. And so I really don't care about the exact result. I just want to see, does it make a true statement when I plug it in or not. And so if I do that here, -5 squared, it's going to give me 25. Minus 5 times -5 is going to give me another positive 25. Then I'm going to subtract 6, and that's supposed to be greater than 0. Well, that's definitely making a true statement. I'm ending up with 44 is greater than 0. So that tells me that every single number smaller than -1 works in my inequality. Now there's no equal sign, so I'm going to use an open circle here, and I'm going to send my graph that way. Now I need to test the middle section of my graph. So I'm going to test 0. I don't have to go right in the middle of those numbers. I'm going to pick the easiest number that I possibly can. When I test 0, 0 squared is 0, minus 5 times 0 is 0, minus 6 is not 0. So I get -6 is greater than 0, which is not true. That is false. So that means I am not going to graph the region in between -1 and 6. None of those numbers are going to work. And then finally, I need to pick a number that's larger than 6. So I'm going to test, let's say, 7. So if I plug in 7, or maybe I'll use 10, easier number. 10 squared, 100. Minus 5 times 10 is 50. Minus 6, is that greater than 0? Faux show, as the kids say. 100 minus 50 minus 6. I again get 44 by coincidence. And so that tells me that the numbers that are bigger than 6 are also solutions. And so we see that we've got this graph. So I'm going to now write that graph in algebraic form. And so this, if we recall from our absolute value inequalities, is an OR problem. So I'm going to write it just like that. X is less than -1, or x is greater than 6. So there's my algebraic answer to go along with my number line answer. Now in this case, we could have used this gray tor device that we used for the absolute value and kind of known that we were going to end up with this type of answer once we found these boundary points. But that's not always reliable, especially if we have an exponent that's higher than 3 or than 2 here, so like 3 or 4. So for that reason, it's good practice for us to use this test approach. Test a number to the left, in the middle, and in the right in order to determine what our solution should be. And so this next example immediately has that circumstance where we've got an exponent higher than 2. So our AND versus OR is going to be a little bit tricky because we're going to have 3 boundary points that we're going to find instead of just 2. Now the first thing I need to do here is I need to first think of it as an equation because I'm looking for the boundary points, the solutions to the equation, and I need to set it equal to 0. So I'm going to move the 3x squared over, minus 10x, I'm going to set it equal to 0, and now I'm going to solve this equation. Well, the first thing I'm going to do is I'm going to undistribute an x, so I've got x times x squared plus 3x minus 10 equals 0. I've still got this x out here, and we don't want to overlook that guy because that's going to contribute to our boundary points. So I've got x, and then I'm going to break this up into 2 sets of parentheses. It's going to be x and x. I need one of each since I'm multiplying to make a negative. Hopefully we see it's going to be plus 5 and minus 2. So when I add those together, I'll get that 3 in the middle. So I have 3 key points. I have x equals negative 5 if I go in order smallest to largest. I've got x equals 0. Whenever we undistribute an x, that means a 0 is going to be a solution. If we just undistributed a 2 or a 5 or a 7, then we could just throw it away. But if we undistribute an x, 0 is a result. And then finally, x equals 2 is going to come out of this guy. So I've got 3 key points, negative 5, 0. I'm going to try to at least keep nominally to scale here on my number line. And so this time I have 4 separate regions I have to test. I'll number them this time. 1 over here on the left, 2 in between negative 5 and 0, 3 right here in between 0 and 2, and then 4 over here to the right of 2. So we just have to go through by brute force here. So I'm going to test region 1. So I'm going to pick a number smaller than negative 5. Again, I'm going to use numbers that are kind of user-friendly to plug in. So I'm going to use negative 10. So if I go negative 10 cubed minus 10 times negative 10, and then check to see if that's less than or equal to negative 3 times negative 10 squared. So negative 10 cubed is going to be negative 1,000. Then it's going to be plus 100. And then I need that to be less than or equal to negative 3 times 100 is going to be negative 300. So I'm getting negative 900 is less than or equal to negative 300. That is indeed correct. So I am going to put a closed circle at negative 5 because of the equal to in my inequality. And I'm going to have a part of my graph is going this way. Now I need to pick a number in region 2. So I'm going to test something in region 2. So I'm going to pick negative 1. That's as easy a number as I can use. So negative 1 cubed minus 10 times negative 1 is less than or equal to negative 3 times negative 1 squared. So negative 1 cubed is negative 1, and then negative 10 times negative 1 is plus 10 is less than or equal to, on this side we're going to get negative 1 squared is 1, times negative 3 is negative 3. So here I'm getting 9 is less than or equal to negative 3. That is decidedly false. So I'm not going to graph anything in between negative 5 and 0. And I'm going to move on to test region 3. So I'm going to again pick a number in that range. So I'm going to use 1. So I've got 1 cubed plus, minus, so I've got 1 cubed minus 10 times 1 is less than or equal to negative 3 times 1 squared. So 1 cubed is 1, minus 9 is less than or equal to 1 squared is 1 times negative 3 is negative 3. So I've got negative 8 is less than or equal to negative 3. That one is true. So that means I'm going to connect these two spots here. So from 0 to 2, that works. And now finally I have to pick a number that's greater than 2. So I've got to test region number 4. So I'm going to, again, pick a number that's nice and easy to work with. 10 works for me. So I've got 10 cubed is 1,000 minus 10 times 10 is going to be 100. So I'm going to get 900 on this left-hand side, and then negative 3 times 10 squared, so negative 300 over here. So I've got negative 300 and positive 900, definitely not less than or equal to. So I'm going to mark that as false. And so my last step here is I've got to write the algebraic answer. So it's not enough to just get the number line. I also want to write the answer in algebra. I'm going to write it in order of how I see it on the number line. So for this part here, I've got x is less than or equal to negative 5. Let's try to make that look like a 5. Or, and then I've got this other group of numbers, and here, because we're bookended on either side, I can write it in that combined format. So it would be 0 is less than or equal to x is less than or equal to 2. So this together is my algebraic solution that matches up with the number line that I arrived from testing the different regions.